Well, hello there once again, and welcome back to my crash course in formal logic. This time we're going to test arguments with indirect truth tables, a very valuable time-saving technique. Now, the basic idea is that some arguments contain so many propositional variables that it's just not convenient to do a truth table. It'd be too long. So take a look at the argument that we tried in the last lesson. Now that argument had 4 propositional variables, and we said that's going to come to a grand total of 16 rows in your truth table. And then we used the half on, half off method, and basically we set up all our T's and F's in the appropriate column. It was a very time-consuming task. But if we took it by the numbers, it all worked out. And that table ended up looking like this. I've highlighted the columns with the premises in the yellow, and over in the orange I pointed out each of the rows that had the conclusions of, well, the rows that had all true premises. And notice we found right at the bottom an invalidating row, one that I've just marked with a star here. Row number 16 is the one that proves the argument is not valid. So what that proves is that there is a way, or a row, or possibility of all true premises and a false conclusion, but it took us a long time to get there. Basic idea of a truth table, we want to get to the point. We should have just been looking for that row 16 and seeing if it showed up in the truth table, or if it would have shown up if we had constructed the entire truth table. So, would there have been a line on that table, if we had done the entire thing, that would have had all true premises and a false conclusion? Now, the strategy is going to be for this: hunt for the invalidating row. I want you to assume the argument is invalid, and if you are led to a contradiction, then the argument was obviously not invalid. It was a valid argument. But if you get no contradiction, then there is going to be a consistent row in a truth table that will have an invalidating set of truth values assigned to the premises and conclusion. So look for that contradiction. Try to prove the argument is invalid, and if you can't, then you obviously have a valid argument. So let's take a look at this example. 2 premises and a conclusion. Step number 1, assume the conclusion's false and the premises true. That is, put an F under the main connective, or if there are no connectives, put the F underneath the sentence variable, or a T in the case of the premises. So I went ahead and did that in each main connective of each premise and conclusion. In the second step, we want to see what values the variables and operators must have when you fill them in. See what you're forced to do. Well, be consistent. Remember, an inconsistency means you've either assigned a sentence letter both true and false on the same row, and assigning an operator a value that violates the operator's truth table definition. So I'm going to go ahead and put a false underneath B, as you can see right here, and look at that conclusion. I can put a T underneath the C and an F underneath the A, because that's the only time the horseshoe turns out false. Now I have to be consistent, so I go ahead and put the same letters that I put for B and A underneath the sentence letters in the remaining premise. Now I can also fill in the value for tilde A if A was assigned a false, and I can also put a T underneath the wedge in that first premise, because the C was all it takes to make that true. Now, after you fill in as many T's and F's as possible, interpret the results. How do you do that? Well, this truth table shows that the argument is invalid. There would be a way row possibility of the premises being true and the conclusion false. I constructed that very consistently. So we know that if we did do a truth table for this argument, in the row that A is assigned false, B is assigned false, and C is assigned true, that's the row in which we're going to get all true premises and a false conclusion. So we would have found the invalidating row if we had done an ordinary truth table. Let's take a look at a second example here. I'm going to put trues underneath the main connectives, or in the third premise of the argument, which is just an A. I'll just put a true underneath that. Now, since I put a true and A in one spot, look at the circle. I have to put a true in that spot as well, don't I? So, going down to this premise, step 2, fill in all that you can for this conclusion. And there's only one way for that to be true. It's going to be if tilde C is true and D is false. Now that automatically tells me what to put under C and D right here. We put falses underneath them. And finally, What are we going to put under B? Well, we're trying to make the second premise true. B implies D. So that tells you that we need to make B false. If we made it true, that would make that premise false. Having done it there, I have to do it here. And that gives me something for the wedge. It's actually pretty interesting. We've got a problem here. Do you guys see it? Is there a contradiction? Look at premise number 1. If that horseshoe claim is going to be true, if A is true, then the disjunction would have to be true as well. That violates our definition for the horseshoe. So we have a contradiction in this argument. The argument is valid. So we could not or would not be, there would not be a way, row, or possibility of the premises being true and a false conclusion. When we tried to assume that, we were led into contradictions, and that's proof of validity. When our attempt to make the argument look invalid winds us up contradicting ourselves. So affirming the premises and denying the conclusion would violate our definition of the horseshoe. So there would be no invalidating row on our truth table if we had written the entire thing out longhand. Now there is a caveat here, a difficulty with indirect truth tables. One row of trues and falses won't always suffice. Look at this conclusion, A dot tilde B in this argument. Now I want to make that conclusion false and see if I can do so consistently. But the problem is I'm not forced to assign any particular valuables to the variables. So when that happens, I can look at all the ways the premises could be true at once, or I can go the opposite route and look at all the ways the conclusion could be false. And the second one is the technique I'm going to show you because it's usually the easier one. So we know that there are 3 ways a conjunction can be false, and I assign values to the variables accordingly. Notice that allows me to handle the B in this argument as well. Now if I handled that, I can certainly go and look at all my premises under each possibility, each of these 3, and find out what values to assign A's and B's here. I'll just assign B the same values that I did way down at the end. Same thing goes for the A's, and I can handle that tilde on the A on the very first premise. So what have we found here? Let's take a look at each one of these. So in the revision of step 4 that I gave you earlier, if any one of the 3 rows is consistent, then we would have found that row on an ordinary truth value table. One inconsistent line invalidates the argument. So the next question is going to be, can we find one consistent row, one consistent way of affirming the premises and denying the conclusion? Well, we got a problem right here. We assigned a truth to this premise, and that violates our rule for the horseshoe. When the antecedent is true and the consequence false, it should have received a value of false. So that one's out of the question. How about this row? Well, it looks as though we've got a true antecedent and a false conclusion once again. That's going to take that one out of the running. And here, once again, we violated the rule for the horseshoe. It doesn't look like we could find any consistent way to to affirm the premises and deny the conclusion. So that means the argument was valid after all. We got ourselves into contradictions when we affirmed the premises and denied the conclusion. Now we need to make an important note here. Notice that in the last example we were forced along each step of our assignments of truth values to the operators and the variables. This indirect truth table that you're looking at now fails to prove that the argument's valid. Why is that? Well, let's start from the beginning. We put in our truths for the premises and falsehood for the conclusion. Step number 1, we have to take what we put under A and C and put it underneath all the other variables. Now what do? Now here's the big problem. We could put a T underneath the B, and then we get all truth for we get a perfectly consistent row. Here's where our two truth tables begin to deviate. In this example, there's a difference. The problem was that somewhere in this truth table that you're looking at right now, a person arbitrarily assigned falsity to a B to get a contradiction and thus to prove validity. That's cheating. Validity only is proven by an indirect truth tables when propositional rules force us to a contradiction, not when our choices force the contradiction. So never make an arbitrary truth or falsity value assignment when consistency is still at stake. Go ahead and make sure you are forced along every step of your, doing your indirect truth table. So you see the basic idea that indirect truth tables can help us handle arguments that would have too many propositional variables to do a standard truth table for. But let's go ahead and take one last example. Let's go ahead and handle this argument that we had in the previous lesson. Rather than do that monstrous 16-row truth table, notice I just put the truth and falsity values that you start an indirect truth table with underneath each of the main connectives for each of the premises and conclusion. Now, obviously at the end there, in order for A wedge C to turn out false, there's only one way that that can happen. Now, having done that, I can put falses underneath the A's and C's elsewhere. Now, the important thing here is to look for what you are forced to do. Here's a few things that I can point out. First of all, we're going to need a false underneath that dot. In other words, we need to make sure that, well, if tilde C is true, and the only way for that conjunction to turn out false is if we have an F underneath the N. And that's going to tell you immediately what to put under that tilde in that in the fourth premise. Now, R is going to have to be false if we're going to get R horseshoe to C to turn out to be true. And that means I have to assign it the same value down here. So this argument is invalid. We got a perfectly consistent assignment of truth values in this argument. We have not violated any rules for the connectives, so we know that when A, R, N, and C are false, that the argument's going to be invalid, and that's exactly what we found on row 16 of our truth table. So basically, we found our invalidating row in a much shorter, much more convenient fashion. Now, are there other uses for direct truth tables? Well, how about we use them to show us single complex sentences tautologous or self-contradictory? We used truth tables to do that before. We can shorten our techniques here. Or we can show that a pair of sentences is consistent or inconsistent with one another. Let's take a look. Now, the strategy for disproving tautologies or proving them is pretty much to assume that the sentence could possibly be false. If you led to a contradiction, then the sentence could not possibly be false. The sentence is a tautology. But if you're not led to any contradiction, then the sentence is not. Let's take a look at a few strategies. Here's one that we tried earlier. We found out that this complex sentence way towards your viewer's right was a tautology. So one thing that we could do is just try to assume that this sentence is false and see if we're led to contradictions. Well, what are we forced to do here? That's the key question. Now, I'm going to have to put a true under the conjunction and a false under the consequent of this horseshoe. And if that's going to be the case, both of the conjuncts of that true conjunction have to be true, including G. Now, if we assign true to G and false to H, obviously I have to give them the same values over here. But notice what that does here. That forces me to put a false underneath the horseshoe. What does that prove? Well, it proves we don't have a true conjunction in the antecedent at all. That means we've got a contradiction of our rules for the conjunction, the dot. So you may be thinking, there is no way the sentence could be false. We got led to contradictions, so no row on a truth table could possibly give it an F. And if that's the case, a full truth table would have proven it to be a tautology if we had written out the entire table, which we saved ourselves the inconvenience of doing. A similar method holds for proving or disproving that a sentence is self-contradictory. Just assume the sentence can possibly be true. That shouldn't be the case for a self-contradiction. So if you are led to a contradiction in your view that the sentence can possibly be true, the sentence was genuinely self-contradictory. If you're not led to such a contradiction, the sentence is not. Let's take a look. Now here's a sentence way over to your viewer's right that we found to be a contradiction. That G wedge H was equivalent to not G and not H. That doesn't sound like it should be true at all. We gave it all F's in its column. Alternatively, we could look for what we're forced to do. Now there are two ways for this biconditional to turn out to be true. One way is if both sides are both the elements of the biconditional are true. Another way is if they're both false. Let's take a look at each one. Starting with row 1, I know that if this conjunctive claim is true, I got to give a tilde to G and a tilde to H. And that means that underneath the G and the H, I'm going to put F's. But notice what that does on this side of the argument, or the biconditional. I just violated the rule for the wedge by making both disjuncts false. So that one leads to a contradiction. And alternatively, if I go to the second row, I'm forced to put F's under the G and H. That helps me know where to put them over here. And then I'm going to be led to truths for the remaining elements. Notice, on this side, I just violated the rule for the conjunction. I put a false where both of the elements of the conjunction were true. So I got led to contradictions importantly in each case. So that means that any way you try to make this biconditional true, you get led to contradictions. That means it is self-contradictory. So once again, we have a much more convenient way of handling these sorts of sentences. We could say there's just no way that the sentence could be true, so there'd be no row on the truth table that would ever give it a T. So a full truth table would have proven a self-contradiction. Again, we just saved ourselves the inconvenience of doing the whole table. Well, so much for showing whether or not sentences are tautologous or self-contradictory. Let's ask ourselves the second question. Can we show that a pair or a set of sentences are consistent or inconsistent? Let's give it a shot. Well, what you have to do is you have to assume all the sentences can possibly be true at once. And if you're led to a contradiction, the sentences are inconsistent. If you're led to no contradiction, the sentences were consistent after all, and you just showed how they could be all true at the same time. So let's give it a shot. Notice we did a truth table for the last two columns over to your viewer's right, in which we proved that two sentences were actually inconsistent with one another. There is no row where they both turn out to be true at once. Well, let's take it by the numbers. What are we forced to do? I'm going to put T's underneath each sentence and treat them all like they're on one row. Now underneath the conjunction, I'm forced to put a T under the K and a T under the tilde. That's obviously going to make the L false. So if I put true underneath K and L underneath the falsehood over on your viewer's left, just to be consistent, what am I forced to? I'm forced to a contradiction here. The rule for the horseshoe states that when a K is true and L is false, this horseshoe claim should have turned out false. So I violated one of the rules for our logical operators, and hence this shows that the two sentences are genuinely inconsistent. So, thinking about it once again, there's no way both the sentences could be true. So no row on the truth table would have given both a T at the same time. So a full truth table would have proven the sentences inconsistent if we had taken the time to do the entire table. Now there's at least one other advantage to indirect truth tables. Sometimes we want to test the consistency of several propositions at once and to see if they're all consistent with one another. The truth table for that sort of thing could get absolutely huge. I'm going to show you guys how to do it, and then I'm going to give you some exercises to prompt you along. So here's two sets of sentences. I'm going to go ahead and put my truths underneath each and every one of the main operators. And we want to see if we can make them all true at once. Now the first example, I have to tell you in advance, it will turn out inconsistent. You will be forced to a contradiction. The second set has, well, you're going to need 3 rows on that indirect truth table. But there will be at least one line in which there will be no contradiction that you're forced to. So I'm going to give you guys some prompts and see if you can guess the values that I'm going to put in. You should be forced each and every step of the way. I'm just going to show you which steps to take. But one thing I do have to do before we get started, because the second batch of sentences contains only horseshoes and wedges, we're going to need more rows for that particular table. In fact, we're going to need 3 rows total, and I'm just going to choose arbitrarily one sentence to work with. I could have started with another one. Are you guys ready to get started? I'm going to point out where I'd like you to put a truth value, and you have to figure out exactly which value goes in that assigned area. You should be forced to that conclusion every single time. Well, do you see any inconsistencies in any of the rows on this truth table? Well, I can point out one pretty quickly. We assigned a true when both disjuncts were false. That's the only time that a disjunction is supposed to count as false. And here we violated the rule for the horseshoe down at the very last row. We assigned a true when we had a true antecedent and a false consequent. But they can all be true at once. There is no inconsistencies to be found in row number 1. So on our truth table, we would have gotten a true for every single one of these sentences when A was false, B was true, and C was true. Well, it looks like you guys have memorized quite a bit of material today. How to do indirect truth tables for arguments, to prove tautologies and self-contradictions, how to show sentences consistent or inconsistent with one another. So I think we'll wait until next time for our next logic lesson, and I'll see you then. Take care.